All right, this is all about Coulombs law. Coulombs law states that an electrical charge exerts a force of attraction or repulsion on other electric charges. Now, I want to point out, and I've got the formula right here. It says F is equal to K Q1 Q2 over R squared. And I wanted to point out some similarities here between Coulomb's law and Newton's law of universal gravitation. If you remember, that was F of G was big G M1 M2 over R squared. These are very similar, except now we're not talking about masses, we're talking about charges. And instead of Newton's universal gravitation constant, we've got Coulomb's law constant. But otherwise, it's really the same formula. You've got two charges, a constant, and a distance between them, and that's going to have some sort of force. Now, I've got on here, it says the force is always along a line connecting the charges. Please don't think that the charges are actually in physical contact with each other. It's just along a straight line path. Okay? Now, one thing to keep in mind, if both charges are the same, so if these are both positive charges, then it's talking about a repulsive force. If the charges are different, then they attract, it's talking about a attractive force. Okay, so that's where this particular force is a little different than gravity. Gravity basically is always attractive. Okay, electrical charges can be repulsive. It's kind of funny. Okay, now down here I've got some pictures. So you might have two positive charges, just charge 1, this is charge 2. You might see some notation in your textbooks or something like that that says this is the force on 1 by 2. This is the force by 2 on 1. You might see that reversed. They might use what I like to call by-on, so it might be the force by 1 on 2. They might have those flipped around. I think for the White Gene Coley book, this is pretty much the notation that we're looking at. For IB, I'm not sure if it might be a little different. I don't know. But for the positive charges, okay, these would repulse each other. Since both charges are in here, they experience the same force of repulsion. If we had negative charges in there, they would also repulse each other. Okay, and then if we had a positive and a negative together, then they would attract each other, and these forces are aimed at them. Okay, just some basic stuff here that we should make sure that we've got down. The Q in each one is the charge. Charge gets units of coulombs. It's a capital C for the letter that would come after the numbers. By the way, 1 coulomb, a 1 coulomb charge is pretty large. Most of the time, we're going to be dealing with like microcoulombs of some sort. Just a reminder, micro is to the -6th. This K value, which is in your packets, is the Coulomb's law constant. It's a given. You don't need to get all crazy about it. 9 times 10 to the 9th. That's a fairly easy one to remember. 9 times 10 to the 9th, although you don't have to remember it because it is in your packet. Newtons times meters squared over coulombs squared. You might run into a question that might say, find the force on two elementary charges. Two similar elementary charges. What they talk about when they're talking about an elementary charge is they're either talking about the charge on a proton or a charge on an electron. Now those two charges are identical, except a proton is a positive charge, an electron is a negative charge. So I've written those numbers in here. I'll have to double check and see if those are in your packets or not. If not, they'll be made available for you. The other thing that we need to remember is that just like when we did Newton's law of universal gravitation and we treated all masses to the center of the mass, we were really treating them as point masses. We're going to do the same thing with charges. We're going to treat them all as point charges. Okay, now so far, this probably seems fairly simple. Okay, if I've got two charges and I know the distance between them, great, I can solve for a force. It gets a little tougher because we might ask you to solve for forces when multiple charges are acting. That type of thing is called superposition. Okay, so adding electrical forces is referred to as superposition. Okay, so we can, and I'm going to describe these. I'm not going to solve anything. We can do that in class. If we do 3 charges in a line, so I've got a -8 microcoulombs, a 3 microcoulomb, and a -4 microcoulomb charge, and they're all in a line, and they're at different distances apart. The pictures that I have underneath here would be, okay, well, this is the force on 1 by 3, this is the force on 1 by 2. Now notice that 3 is a negative charge and 1 is a negative charge, so that's repulsive, so it's going to push it away. Whereas 2 is a positive charge, so if you got a negative charge and a positive charge, those are going to attract, so this force on 1 by 2 is an attractive force this way. If we look at the forces on the positive one, well, it's going to be attracted to the negative charge and attracted to the negative charge on this side. So this is really in a tug of war. It's going to be either pulled this way or pulled this way, whichever one can supply the greater force. Now, if you look at the two numbers, you say, okay, this one's -8, so it's a bigger charge than -4. But this one's also further away. So we'll actually have to do some calculations to see which ones are different. But you're going to have to really find the difference. If we wanted to find the total force on the positive charge, we'd have to find the difference between F21 and F23. Okay, they get tougher, of course they do, if we start putting them at angles. If we put charges at angles, now we just have to start evaluating them along both x and y axes. So if I've got 2 positive charges here and a negative charge over here at a right angle to this particular one, there's angles between all these things. And along the x direction, okay, if we're trying to find the force acting on this one, there's an attractive force here that lies solely along the x-axis. So I've written an expression here that says the force, and I probably should say the force in the x, is K Q3 Q2. This is Q3, that's Q2. Okay, all over the distance between them squared. There's going to be an attractive force there. There's also going to be an attractive force here, but if I'm only going to look at it on the y, or I'm sorry, on the x, I only really want this component of it. So I'm going to have to add K Q3 Q1.6, that's the difference between them squared, and I only want this component, so I'm going to take the sine of 60 of that particular value. That's going to give me the total attractive force in the x. In the y, well, it's only attracted vertically by this one right here, because along this one it's all along the x-axis. So to solve for that one, again, K Q3 Q1 divided by 0.6 squared, that's the distance between them. And I'm going to take the cosine of 60 because that one gives me this particular component, the vertical component. Once you have those two forces, if it acts for the total force, then that total force would have to be the square root of f of x squared and f of y squared from whatever answers we get over here. Okay, so that's where it can get a bit more tricky.